do an elastic collision example. Okay. So, let's say we have an oxygen atom. And we shoot the oxygen atom with a helium. Okay, so this is the nucleus. So we have an oxygen nucleus. We shoot the oxygen nucleus with an alpha particle. So that'd be the same mass as a helium nucleus. So let's say that this has an initial velocity of, let's say it has an initial velocity of 2.65 times 10 to the 5th meters per second. And so what happens is, because this has got charge, plus 4 fundamental charge, and this has charge plus 16 fundamental charge, they repel each other. So the closer they get, the more the repulsion. In fact, the repulsion gets if you get half as far apart, it's 4 times more. So the repulsion actually gets so great, they don't actually make contact. So the helium nucleus never actually hits the oxygen nucleus, but they repel, and then it gets pushed back, and the oxygen gets pushed this way. So afterwards, the oxygen is moving this way with some velocity VO for oxygen. The helium is moving this direction with some velocity VHE for helium. And so I want to know what are those two velocities. So we got the helium moving in, we've got the oxygen up here, and so conservation of momentum. The mass of the helium times the initial velocity equals the mass of the helium times the velocity of the helium afterwards plus the mass of the oxygen times the velocity of the oxygen afterwards. Well, we know that the helium mass is basically 4 atomic mass units, and so we can just put 4 in here, and the oxygen is 16 atomic mass units, so we can put in 16 right there. Okay, we divide everything out. V sub I equals V sub HE plus 4 velocity of the oxygen. So I want to isolate one of these, our two unknowns. So there's one of the unknowns. That's equal to the initial minus 4 times the velocity of the oxygen. Okay. Well, because the electrical force is conservative, then that means that we know that the initial kinetic energy is going to equal the final kinetic energy. So 1/2 mass of the helium times the initial velocity squared has to equal 1/2 mass of the helium times velocity of the helium squared plus 1/2 mass of the oxygen velocity of the oxygen squared. So the 1/2s all cancel. So again, same thing. We've got 4 atomic mass units and 4 atomic mass units times velocity of helium squared plus 16. We divide through by 4s. That makes that a 4. So VI squared equals the helium squared plus 4 V oxygen squared. Now, we know that the helium velocity we had derived was VI minus 4 velocity of oxygen. So the velocity of helium squared is going to be VI squared minus 8 VI VO plus 16 VO squared. So we take that and plug in right. So VI squared equals VI squared minus 8 VI VO plus 16 VO squared plus 4 VO squared. Okay, so these cancel, so 0 equals minus 8 VI VO plus 20 VO squared. So that cancels one of those. Okay, and so we do a little algebra here, and we find that VO equals 0.4 VI. Okay, well, we know what VI is, so that means that the oxygen is moving afterwards at 0.4 times 2.65 times 10 to the fifth meters per second. So the oxygen velocity is going to be equal to 1.06 times 10 to the fifth meters per second. Okay, now we go back and we say, oh, but wait, we've already calculated that, derived that the velocity of the helium is the initial velocity minus 4 velocity of the oxygen. So if we plug in that, that would tell us that this is equal to minus 1.59 times 10 to the fifth meters per second. Okay, so that means we have this helium coming into the oxygen. It's initially moving at 2.65 times 10 to the fifth meters per second. It hits the oxygen. The oxygen goes shooting this way. The helium goes bouncing back that way. And so the helium is bouncing backwards at 1.59 times 10 to the fifth meters per second, and the oxygen is knocked forwards at 1.06 times 10 to the fifth meters per second. And so that's an example of that's an example of an elastic collision.